Hello, my name is Eric Heim. I'm the principal investigator on this project called Knowing When You Don't Know, AI Engineering in an Uncertain World. This project started last year, so we're in our first year. We just finished our first year, and we'll continue for the next 2 years. So at the core of this project is this idea of uncertainty in model prediction, specifically ML model predictions or machine learning model predictions. And we argue that quantifying and reasoning about this uncertainty is a key component for informative and robust AI systems. And so I'll be using this example throughout this talk of a object detection at the ground level, specifically of vehicles, motivated by some of the applications we have here at the AI division. But honestly, you can think about a lot of the concepts that I'm going to talk about today, not just within this application, but with many others. So if you have questions at the end of this, please feel free to ask me about how this work applies to your particular missions, or if you care to think about not this application that I talk about it or some other, please feel free to do so. But in this particular application, we have something, say, a autonomous ground robot that's doing some surveillance of some area. And for this particular task, it's common for an ML or machine learning model to do is something called object detection. So an ML model will make a prediction such as this, where it localizes or predicts the position of an object denoted by this bounding box here, as well as what this object is, the class of this object. In this case, it's a friendly truck. And such a prediction can be useful for intelligence analysts for predicting where potential assets or enemies are in some particular mission that feeds to some analysts to do some analysis. And while this is pretty informative, it can make predictions and inform such intelligence system or intelligence tasks, but it provides a very definitive statement about what the model thinks is reality. And what's potentially more useful in this situation is this idea of not just expressing what the class of that object is, but its confidence. So potentially more informative to an analyst is not just that the class is a friendly truck, but how confident, on a scale, in this case, from 0 to 1, of that prediction that the model is. And so considering that this friendly truck, this model is predicted with confidence, this model predicts friendly truck with confidence, say 98%, is very different than, say, around 35%. And this is something that the analyst can consider when considering the next steps in their task. And so that's why we say that accurate estimates of these uncertainty estimates of machine learning model predictions can lead to better informed decision making. But that's not the only thing. If you look at the larger context of an AI system for which this machine learning model may be a component of, you can consider other usage of uncertainty. Specifically, if you consider not just the ML model's predictions going directly to an analyst, but to say give some situational awareness in some larger system depicted here by this map, where in the bottom left-hand corner, there's this triangle that represents the robot that's facing the road here. You can imagine a similar model being able to inform in such a way. So for instance, the model may be able to make the prediction, again, that there's a friendly truck that's detected in a location. And by doing so without understanding the confidence of this, it could say with definitive statements about reality that the friendly truck is in this location, say on this road. But again, this is fairly limited. But if you consider confidence, you can actually do different things. So for instance, you could threshold the confidence in such a way that if the confidence is over some threshold, such as 0.5, what you could say is, yes, we are confident enough about the prediction that we can say that this is a friendly truck at this location. But if you're not that confident, if you're below that threshold, you could say things like, hey, we know there's something on this road, but we're unsure about this class. And to gain confidence or to reduce uncertainty, you can then maneuver the robot to gain this idea of confidence, to get a better view of this, or task other sensors. So this is why we say that allowing higher level reasoning in AI systems access to this model predictive uncertainty, these systems can be more robust to the failures that are caused by unconfident predictions. So in this work, we focus on evaluating, characterizing, articulating, and rectifying uncertainty in machine learning models for the purpose of more informative and robust AI systems. Specifically in this talk, we'll talk about this concept of calibration, and more specifically, how you evaluate ML models or ML classifiers for their calibration. So just to start off with what the idea of calibration means, we'll start with a similar example as I discussed before, where a classifier is trying to predict friendly trucks versus enemy tanks. And in a deployed scenario, a new image or a new instance comes into the classifier, and the most common output from, say, for modern neural networks that are commonly tasked to do these types of tasks is some idea of predicted confidence over each class. And so in this case, it's expressed as a probability. So say 0.6 probability that they think that this input is a friendly truck versus enemy tank. And the question is, how do we understand these values? Classifier calibration poses this, or answers this question by saying that these values are backed by the frequency of class labels. And what does this mean? This means for a classifier to be perfectly calibrated, for all possible inputs, the class for which the classifier outputs 0.6 and 0.4, 60% of the time the input should be a friendly truck, and 40% of the time the inputs should be an enemy tank. And so what this actually backs these values with is this idea of historic empirical frequency of the actual classes over the domain of instances or images in this case. So given this particular definition of classifier calibration, we not only can understand these values that are coming out of these classifiers in a particular way, but we can also evaluate our models according to this definition of calibration. And so this has gotten a recent attention within the ML community, or the machine learning community, due to the fact that there's observations about the deficiencies of modern neural networks for their calibration. But most of these works actually focus on this particular metric for evaluation called top one expected calibration error. And there's a lot that goes into this metric, and a lot of the metrics we'll be talking about today. But the point here is that we want to highlight one particular characteristic of top one expected calibration error, for which potentially can cause issues within particular mission contexts. And so, as an example here, now we're predicting this classifier is tasked to predict not just 2 classes, but 4, ranging from friendly tank to friendly truck to enemy tank to enemy truck here. The model will then output 4 probabilities. In this particular instance, the most probable class is this friendly tank at 0.6. And so according to this top one expected calibration error metric, this is what this model is being evaluated for. It's saying a perfectly calibrated model under this top one expected calibration error is that for all inputs for which the classifier outputs 0.6 as the most confident class, or the highest value that it outputs, 60% of the time, those inputs should be that class. So it's basically reflecting this idea of making a prediction of the highest confidence class, and the confidence associated with that should be calibrated. Now, that's great if you're only going to consider the most confident class, but consider the following scenario. You have 2 classifiers. Both of them have the same most confident class here, but the rest of the probabilities output by the models are different. Now, according to top one expected calibration error, these 2 classifiers are considered the same. However, when you look at the other probabilities, these can mean very different things within mission context. Specifically, the second classifier, the one below the top one, the class of enemy tank actually has a probability of 0.4, which is very different potentially to an analyst than saying the top model saying there's only a 5% chance of enemy tank. So it's important to recognize the fact that this particular metric that's most commonly used within the machine learning community to evaluate their model calibration actually doesn't reflect certain mission contexts that are important for the practical usage of these models and the usage of their confidence. So this work, which is representative, which some of the work I'll talk about today is represented in this work we have that's currently under review, we're focusing on this idea of developing metrics for calibration that are more closely match certain contexts in which models are deployed, these classifiers are deployed. So we take a particular statistical framing of expected calibration error and create a larger framework over this, as well as develop specific metrics in that framework and highlight how they can be used. And so these consider a couple factors, namely application-specific trade-offs, such as we want to see how it's not just the calibration between particular classes, but between the idea of groupings of friendly vehicles versus enemy vehicles. See how the calibration reflected across those particular groupings. Things of specific instances of interest. So if we want to evaluate just for instances for which the ground truth real label is enemy vehicle, we can isolate those instances within our metrics to see specifically how our model is calibrated on enemy vehicles. And the last two I'm going to talk about with some examples from our paper here. But the first one is this idea of either focusing on the most confident class versus the full probability distribution. There's a whole gamut of considering the probability distribution in different ways that's sort of in between these two. And so we ran an experiment where we wanted to evaluate the current state of the art in classifier calibration according to these more context-focused metrics and observe how they perform compared to the traditional ways of evaluating expected calibration error. And so in our first experiment, we developed this metric that's called top K expected calibration error. And the base setup is this. We train a residual network, neural network classifier that's 50 layers deep. This is a very common architecture used for this task. And we train this model on a data set called ImageNet, which is a standard image classification benchmark used within the machine learning and computer vision community, which is to classify these images as one of 1,000 different classes. And we wanted to see, again, how these methods, these calibration techniques, compare to the baseline with respect to not only the traditional ECE, but also these other context-focused metrics. And so there's a lot going on this graph right here, but to break it down just really quickly, on the x-axis here, what you're seeing is groups of bar charts that were reflective of the base classifier. So this is just the ResNet 50 trained on ImageNet with no explicit calibration being performed, versus each of the other groups represent a particular calibration technique being applied. And on the y-axis, the bars represent the expected calibration error. So you're more calibrated for a lower bar. And on the key denotes the particular metric being used. And so if you just take a look at the blue bar here, what you see is, according to the traditional top 1 expected calibration error, that all of these interventions with exception of focal loss actually do indeed reduce the traditional ECE. So this is just as advertised, and this is representative of the work that's currently out there. But if you consider more of the probability distribution, not just the most confident class, but say the top 5, well, you see the story is actually very different. And so this particular scenario where you're showing the top 5 could reflect the case where instead of showing an analyst just the most confidence class, you're showing it the 5 most confident classes. So providing them more information to make decisions. And in this case, the gap between the base model where there's no explicit calibration being performed versus these techniques that are trying to calibrate the model is either lower, they're closer together, or in the case of label smoothing, denoted LS here, is actually higher expected calibration error in these cases. And in the case where you consider the full probability distribution, again, it actually increases by quite a bit more. So the model, the interventions, or these calibration techniques either increase expected calibration error over the full output of the models, or perform about the same. And the point here to understand is that the top 1 or traditional expected calibration error is a particular view and assumes a particular usage of these classifiers. While if you look at more of the probability distribution, some of these calibration techniques that are explicitly reducing traditional ECE are indeed doing that at a cost at other different views of calibration, such as the top 5, or calibrating over the full probability of all classes. And so for the other experiment I wanted to show today, we wanted to show something that mapped to a particular use case. So a scenario in which you can use confidence in a realistic setting. And so what we chose to do is highlight this particular metric that we're calling inter-interval ECE. And to do this, we trained, again, that residual network, the 50-layer residual network, on this data set that is chest x-rays of patients that are going into hospitals that either have COVID or not. So the classification task is to classify whether this chest x-ray came from a COVID patient or not. And so you can imagine a scenario where such an automated system could facilitate the diagnosis for a clinician of COVID. But in this case, we're going to make the assumption here that the confidence values that are expressed in these predictions are not just the exact values of confidence that are produced by the model, but instead are organized in categories ranging from very low confidence to very high confidence. And what this means for the model is if you have, say, a confidence output of between 0.0 and 0.2, this corresponds to a very low confidence category. And so instead of the exact values, a clinician would see from the model very low confidence. This is very common within the human factors community because humans tend to understand these categorical notions of these continual values more than specific values such as 0.5, 4, 3, 6, 7, right? That's much more difficult for a human to understand than something like low confidence. Anyway, the point here is we want to see how to evaluate this model with this particular assumption on the context in which the model is going to be used. So here's the same diagram I showed before, except for now the bars represent the traditional expected calibration error again for this COVID CRX2 data set. and then as well as these interval-specific ECEs. And so if you focus again on just the traditional ECE, you can evaluate your model with, again, that particular assumption on interpretation of the outputs of the model. And we see here, roughly speaking, most of the models behave roughly the same, some slightly better than the baseline. But if you look at these more specific interval-specific expected calibration measures, you can actually see much more insight into the model. So if we focus just on focal loss here for a second, what we see here is the green through the blue bars, so the second, third, fourth, and fifth bars here from left to right. We see that there's errors that measure specifically the error of a model if it produces a value that is supposed to be in the low confidence region, say for instance for the green bar there, that is actually the degree in which it violates that assumption of being into that confidence category. And what we see here is that the model is actually very good at producing values that are representative of low confidence or high confidence in COVID. But in the middle here, where potentially the more confusing cases that a clinician may need to have the model express this uncertainty for, is actually the model is more poorly calibrated. And so this provides a specific insight into this particular this calibration technique that traditional ECE simply cannot provide. And that's sort of the point here that I wanted to show in this experiment, in that by using this framing of expected calibration that we produce, you can actually have metrics that reflect classifier usage, and so that you can better evaluate your model for how it will actually be used. Yeah, so this is, like I said, this is work that's been produced that's currently under review with support of many of the awesome people at the SEI on the team, depicted here in the top row as well. I didn't get to talk much about our work with our academic collaborators, R.T. Singh or Zach Lipton, but that's definitely part of the work, and we're super stoked to work with them. And if anybody has questions about that work, we can talk about it. But just to wrap things up, the point here is that machine learning models are able to express their uncertainty in their predictions, and that can lead to more informative, robust AI systems, specifically through allowing humans to reason about this uncertainty to understand when the model is likely to be incorrect in its predictions. And also, by incorporating this uncertainty in a larger AI systems to take different actions based on model confidence, potentially resulting in more robust AI systems. As a larger view of this project, we're trying to evaluate models for their uncertainty, characterize that uncertainty, articulate that uncertainty, and rectify that uncertainty in models. And again, if there's any questions at the end of the talk, we can certainly discuss those particular parts of the project. But what's going to be next that we're going to focus on is, one, develop a demonstration highlighting the utility of these models expressing this uncertainty in sort of a more tangible application that's more focus on a particular application that highlights this utility. And this actually involves this idea of articulating uncertainty in a way that a human can understand, as well as, our model certainly needs to be able to express it, and we want to evaluate our model for its ability to do that. So that's something that's on the horizon that you guys can look out for. But also, we didn't talk a lot about sort of this idea of characterizing uncertainty. In some sense, there's different sources of uncertainty in ML models. So there's different reasons why models can be uncertain. So characterizing that uncertainty, so you'll be able to more accurately quantify it, but also be able to rectify it within your model, is super important and something we're going to be working on coming up here. And the last thing I want to mention is, while we have some collaborators throughout the DoD and actually in academia and elsewhere, we're always looking for more real-world use cases of this work. And so if you have a mission need for machine learning models that express uncertainty, definitely give me a call. We're always interested to hear about mission applications. And so my email's there depicted at the bottom. Feel free to drop me a note. Thank you.